Okay, this short set of slides is to help you to, to make systematic picture of how we calculate results from different types of calibration. They are reasonably simple. I presume that you'll be using Excel for all the calculations, no matter how simple they are. You want to look at all these examples through your textbook, please. So first, we have our example we were looking at before for calibration data for chromatographic determination of isooctane in hydrocarbon mixture. So we had 5 calibration points. Peak area from chromatogram was collected as a function of mole percent of isooctane. Then we did calibration in Excel, getting slope and intercept. Now, how we can use this data? We can do one sample. Students always say unknown, but in professional area we say sample. And we do it 4 times, having peak areas of 288, 285, 283, and 282. These numbers, of course, are not identical, but close enough to each other. So how we will process this data? The only things we need from our calibrations is slope and intercept. So, again, how we calculate and present our results. So we have our slope and intercept, and we have our numbers. Our calibration equation was A, area, is K, X plus B, where K was slope and B was intercept, A, our measurement, and X concentration, which we want to calculate. So we solve it over X. X is A minus B divided by K. Now we know K, we know B, so for each A we can calculate X. It's very easy formula in Excel. A minus B divided by K. And do it 4 times, exactly identical. As you can see, we have 4 slightly different numbers. After that, we calculate mean, standard deviation, and lower and upper limit of confidence interval, exactly as we did for usual data. Now we write the result with proper number of significant figures. Looking at our standard deviation, we need 2 figures after dot. So confidence interval in mole percent will be from 1.21 to 125. Or alternatively, I could write the same information as 123 plus minus 0.02. This and this shows the same information, whichever you prefer. Next, we use single standard calculation. We are not making calibration, but we already know that calibration would be linear. This is a risky approach, but it's much faster, of course. So I'm doing one standard. In this case, for 0.25 milligrams of iron, some procedure gave absorbance of 0.961. Blank was 0.001. Now, the sample was done exactly the same way, giving me this result. I look at my procedure. I recall that I need subtract blank from my standard and from my unknown, and then calculate mass of iron in unknown as mass of standard, signal from unknown divided by signal of standard. So hooking the numbers, I have 250 multiplied by signal of unknown 567 minus blank divided by signal of standard minus blank 961 minus 1. I'm getting my result. If I am doing it several times, I will process my results exactly the same fashion. Next procedure, standard addition. I consider the case with 0 blank for simplicity. If it's not 0, we do like in a previous example. So I have my sample, 0.567. Then 0.25 milligrams of iron was added to this sample, giving me new absorbance, which is larger. And now formula is different because our standard gives us a fact that is difference between this and this number. So the formula will be 0.250, that's my addition, and 0.567, 961 minus 567. As you can see, the number is very different from our previous example because, of course, the procedure is absolutely different. Please be very careful and never mix standard addition with single standard. They look the same, but they are very different. Of course, it's a good idea to have several standards for standard addition procedure or even for single addition procedure. In that case, we have better statistics and we can say the standard deviation of our results.